In the next unit that we're going to take a look at in regards to exponential equations, we're going to start by taking a look at expressions that need to be solved, or rather simplified, using properties of exponents. So again, we're going to be looking at expressions that involve exponents that we're going to try to simplify. In order to do that, we have to have a working knowledge of several different properties of exponents. So what we're going to do is first we're going to take a look at each of these and illustrate how each of them work. So the very first property we have right here, we'll call this property number 1. It says x to the n times x to the m equals x to the n plus m. What this one is saying is if I have two base values that are the same, I can combine them, I can multiply them together, but I have to add the exponents together. So for example, if I have p to the third times p to the seventh, that is going to equal p to the 3 plus 7, which equals p to the 10th. So if I have the same base value raised to a different exponent, I can combine the two. I can multiply the two bases together and I add the exponent, and it becomes p to the 10th. Okay. Property number 2 here illustrates that if I have a rational piece, an x over y, a fraction, quantity raised to the n power, that exponent actually belongs to both the numerator and denominator. You can see over here it belongs to the x and it belongs to the y in the numerator and denominator. So we can illustrate this maybe by taking a look at something to the effect of t divided by 4 quantity squared. So in this case, because the complete fraction is in parentheses squared, that squared belongs to the numerator and the denominator. So we could write this as t squared over 4 squared. And simplifying the bottom, we get t squared over 16. So again, when you have a quantity squared, or a quantity raised to an exponent, that exponent belongs to both the numerator and the denominator. Next property we have here, property number 3, does the same thing as property number 2, but in the context of multiplication. It says here if you have one base value multiplied by another base value in parentheses, so associated with each other, and the exponent is given to the entire set in the parentheses, that exponent n belongs to both bases inside the parentheses. So we might illustrate this by doing something like 3x to the third power. That third power belongs to everything in the parenthesis, both the 3 and the x. Now notice that it belongs to everything in the parenthesis if everything inside is multiplied. Notice there's no addition or subtraction between components in the parentheses. It's all multiplication. And up in number 2, it was all division. If multiplication and addition, if addition and subtraction are involved, this property won't work anymore. So in this case, that third power, third exponent, goes to both 3 and it goes to the x. So simplifying the 3 to the third, that becomes 27x to the third. Property number 4 here is similar to property number 1, except that we're dealing with the division of two common or similar bases rather than the multiplication of two similar bases. So to look at this one, we might illustrate this by doing p to the 5th over p to the 3rd. Now what this property is illustrating is if I have a common base, here x and x, I can combine them into a single x, but notice what I'm doing with the exponents. M minus n, I'm subtracting, but I have to do it in the order that it's showing. It's going the top exponent minus the bottom exponent. So in our example here, this would be p to the power of the top exponent 5 minus the bottom exponent of 3. That ends up giving us p squared. This fifth property here we're going to hold off on. So let's jump to the sixth property right here. The sixth property is an interesting one. We essentially have a stacked exponent. We have x to the n to the m. So x is raised to the n and it's raised to the m. Well, if I have two exponents that a single base value is being raised to, I multiply, as you can see in this property, I multiply those exponents together. So for instance, if I had r to the third to the fourth, because r is raised to the third and to the fourth power, I multiply those powers together and I get r to the 12th. Just like property 5, property 7, and 8 here, we're going to hold off until we get to problems that involve those. So we've looked at 5 properties total. What you're going to find is more often than not, you're going to be looking at those properties in conjunction with each other. Very rarely will you do one at a time. Most of the time you'll be doing them, combining them in one operation. So let's go ahead and take a look at some examples. We want to simplify the following expressions using those properties of exponents. So the first example we have here is 2x to the third raised to the fourth power times 7x to the sixth. Okay. Now I have a methodology here. There's nothing set in stone about this methodology. It just helps organize the way I do it so that I can apply similar processes to problems to make sure that I'm keeping track of everything that I'm doing. So the very first thing I recommend doing is simplifying any parentheses. So right here, notice I have a set of parentheses. Is there anything in the parenthesis that can be simplified? Now 2x to the third is as simple as it's going to get. However, I do have a fourth power on that parenthesis. So what I'm going to do is I'm going to use the property that says, I'm going to use two properties together. If I have x to the n, or rather x times y to the n, it equals x to the n, y to the n. Okay, so this 4 belongs to both the 2 and the x. I'm also going to be using the property that says if I have x to the n to the m, that is equal to x to the n times m. That's going to come into play when I bring this 4 into the x, because the x already has an exponent on it. So this 4 comes into the 2, that's 2 to the fourth power, and then the fourth exponent also comes into the x. But because I already have a third power there, I have to multiply the exponents together. 3 times 4 is 12, times 7x to the sixth. I'm now going to simplify that 2 to the fourth, which is 16. So 16x to the 12th times 7x to the sixth. Okay. So it's simplified fairly decently already now. I want to now continue my simplification process by simplifying everything in the numerator and denominator separately. Well, I have no denominator, so just take a look at the numerator. So first I want to multiply. Since everything is multiplied, I'm going to multiply my constants together. 16 times 7. 16 times 7 produces 112. I'm then going to multiply my x's together. Now if we remember, if we multiply a common base together, what do we do with the exponents? We have to add the exponents together, as in that property that we saw up there, and I've rewritten right here. So that becomes x to the 12 plus 6. That becomes 18. So we've successfully now simplified this as far as we can. We have no more constants and no more common variables to combine. Okay, let's continue and take a look at some more examples that use some of the other properties. Our next example here is negative 3x to the ninth all over 9x to the third. Okay. So the first thing that we saw in our methodology was to take a look at any parentheses. I don't have any sets of parentheses here, so I'm good there. Next it said to look at the numerator and denominator separately. So if I look at the numerator here of negative 3x to the ninth, there's really nothing to simplify there. If I now look at the denominator, 9x to the third, again, not much to simplify there. That third step in the methodology above was to start now combining numerator and denominator components that are like. So for instance, this negative 3 over 9 could be reduced to negative 1 over 3, because negative 3/9 is negative 1/3. And then also, the common base of x. We have that property that says if you have x to the m over x to the n, so a common base of n, you can combine into a single n, but what do you do to the exponents? You subtract. So this becomes x to the 9 minus 3, which is 6. Now notice the result of that is in the numerator. Whatever the subtraction ends up being, that piece ends up in the numerator, whether positive or negative. So we've combined everything we can, numerator and denominator. Now I'm looking at this negative 1, I can clean this up a little bit and just write it as negative x to the 6th all over 3. And I have no more common constants and no more common variables to combine anymore. Great. Let's continue and take a look at another example. So this example, we've got two sets of parentheses to deal with right off the bat. Now we're going to have to be careful here because we've got negatives floating around in a lot of different places. So here's how we're going to approach this. Let's look at each set of parentheses separately. Let's first look at this first set of parentheses. Now we know that property that says if you have a quantity in parentheses and everything is multiplied together like we have in these parentheses, that this exponent belongs to every piece. It belongs to the negative 4, it belongs to the v, it belongs to the h. So let's give it to the negative 4. I'm going to be careful here. I'm going to put my negative 4 in parentheses so that I know that it's negative 4 squared, not just 4 squared with a negative tacked on. I then have v to the 5th. I have that squared coming into it. So if I have v to the 5th squared, I have to multiply those two exponents and I get v to the 10th. Lastly, I have h to the 3rd squared, again stacked exponent. 3 times 2 is 6. This is then being multiplied by our second set of parentheses. Okay, here I have this second set of parentheses all being raised to the exponent of negative 1. Now again, this negative 1 belongs to every piece, the negative 5, the v, and the h inside the parenthesis that it's associated with. So I'm going to give it to the negative 5, again being careful to put that in parentheses. I'm going to give it to the v. Now v squared to the negative 1, again stacked exponent, I have to multiply. That becomes v to the negative 2. The same thing happens with the h. It already has a squared, and then it's raised again to the negative 1. So that becomes h to the negative 2, because 2 times negative 1 is negative 2. Now, this problem illustrates a property that we hadn't taken a look at yet. The property said this: if I have x to the n, it's the same thing, or x to the negative n, sorry, it's the same thing as 1 over x to the positive n. In other words, what this is illustrating is this: if you have a negative exponent, you can move it back and forth between numerator and denominator, and it'll switch the sign on the exponent. In other words, a negative exponent becomes a positive exponent. So, we don't like to leave negative exponents anywhere in a problem. So we're going to take these negative exponent pieces, and every piece that has a negative exponent on it, we're going to end up moving to the denominator. So we end up with, negative 4 squared really quick. Negative 4 times negative 4 is 16. V to the 10th, h to the 6th, divided by every piece here that has a negative exponent is going to move to the denominator. So that's negative 5. But because I'm moving it to the denominator, it's not to the negative 1 anymore. It's to the positive 1. And then this becomes v to the positive 2 and h to the positive 2. Great, so we've got rid of all of our negative exponents. I see in the bottom already that negative 5 to the first power is just negative 5. So I'm going to simplify that so we don't have that floating around anymore. What I also see is that I now have sets of common variables, v and v, and h, where division is in the works. So I'm going to do that combination through division. So I leave the 16 over negative 5. Now I'm going to look at the v's. Again, if I have x to the m over x to the n, that equals x to the m minus n. So I have to take the top exponent of 10 and subtract the bottom exponent of 2. 10 minus 2 is 8. So this becomes v to the 8th. I'm going to do the same exact thing here with the h's. So it's going to become h to the top exponent of 6 minus the bottom exponent of 2. 6 minus 2 is 4. So we end up with 16v to the 8th, h to the 4th, all over negative 5 as our final simplified expression. Well, we have two more examples that we want to take a look at. This first example just combines a lot of what we've seen already and gets us used to these negative exponents again. And then the last example illustrates a final concept. So let's go ahead and dive into this second to last example. Okay. My methodology above said to take care of parentheses first. So I'm looking inside my top parenthesis, 3x to the negative 2, y to the negative 2, quantity to the squared. There's nothing in the parentheses to simplify, but I can bring this squared on the outside and give it to the 3, the x, and the y, everything in there, because everything is multiplied. So in my numerator I have 2y to the third, but then I also have now times 3 squared times x to the, now negative 2 times 2 is negative 4, times y to the, again, stacked exponent, y to the negative 2 to the squared is y to the negative 4. Multiply the exponents. And all of this is divided by now what we have in the denominator. Okay, again, I have an exponent on a parenthesis. That exponent belongs to every piece, the negative 3, the y, and the x. So I'm going to give it to the negative 3. It's going to be negative 3 to the negative 2, and y to the negative 2, and x to the, well, x already has an exponent of 2, so 2 times negative 2 is negative 4. Great. So I'm going to clean up some of the constants here and combine what I can in the numerator. In the numerator I have 3 squared, which is 9, and then 9 times 2 is 18. Then I also see that I have 2 y values multiplied together up in the numerator. So those 2 y values I can combine into a single y value through multiplication. But what do I do to the exponents? I have to add them. So 3 plus negative 4 is negative 1. 3 plus negative 4 is negative 1. And then I still have the x to the negative 4th in my numerator. Divided by, well, constants to negative exponents are a little tough to deal with, so we're not going to deal with that one quite yet. We'll do negative 3 to the negative 2 power still. Then I have y to the negative 2 and x to the negative 4. Okay. So what I'm going to do here now is I'm going to take a look at my common bases. I'm going to take a look at my common base values. I see a common base value here of y, and it's being divided. So what I'm going to do is I'm going to keep my 18, and I'm going to keep the negative 3 to the negative 2 power. But I'm going to look at my y's. What does my y become? I can combine through division and end up with y to the negative 1 over y to the negative 2. I know I have to do my top exponent of negative 1 minus the bottom exponent of negative 2. Now be careful here, because what we're dealing with is negative 1 minus negative 2. Now this is really negative 1 plus 2 because of the double negative, which equals positive 1. So this becomes y to the first power. Okay. Now I see a common base of x. But what I notice about this is that it's the same exponent top and bottom. When it's that case, I know since I have the same thing, they both cancel each other out, and my x's are gone. So here I'm left with 18y to the first power over negative 3 to the negative 2. I want to now deal with the fact that I have a negative exponent. So to deal with that negative exponent, I know from the previous example that wherever it is, if it's in the denominator, I can move it to the numerator and the exponent sign switches. So I'm going to rewrite this as 18y times negative 3 to the positive 2. When I move it from denominator to numerator, the sign of the exponent changes to positive. And I have no denominator left. So now it's just simplifying this final constant piece. Negative 3 squared is a positive 9. Negative 3 times negative 3 is 9. And then we do our 9 times 18, and we end up with 162. So this then becomes 162y. So all of that simplified to a nice, easy, simple, straightforward expression, 162y. Great. Last example. The last example is going to illustrate a specific property. You'll notice that there is a 0 exponent. So the property that deals with that said that if you have x to the 0, it equals 1. In other words, anything to the 0 power is equal to 1. So if I had 10 to the 0 power, that equals 1. If I had 32 to the 0 power, it equals 1. It doesn't matter what you have raised to the 0 power, it's 1. Now the one situation that I want to bring up here is this. If I have negative 4 to the 0 power, that equals 1. Anything to the 0 power equals 1. However, if I rewrite this without parentheses and go negative 4 to the 0 power, that 0 power only belongs to the 4, and that negative is not involved in it. So this actually becomes a negative 1. So keep that in mind, because that's what we have in our example over here. Okay, so taking a look at what we have over here, if you see a 0 exponent, always deal with that first. So in the numerator, I have 2x to the negative third. And in the denominator, I have 2y squared. And then in the parentheses, I can simplify that piece. Negative y to the 0 power. Because the negative y, yes, it's in parentheses, but so is the exponent of 0. So what we really have is negative y to the 0 power, which means it's y to the 0 power with a negative tacked on. So this becomes a negative 1, and then what that simplifies in the parentheses is then raised to the power of 2. So negative y to the 0 power just becomes negative 1. Okay, so we end up with now 2x to the negative 3 all over, negative 1 squared is positive 1. Positive 1 times 2 is 2. So we end up with 2y squared in the denominator. Okay, I first see that I have constants that I can simplify. 2 over 2 cancels each other out, and I'm left with x to the negative 3 over y squared. The last thing I need to do is deal with that negative exponent. If I have a negative exponent in the numerator, I know that I can take and move that to the denominator. So I have just 1 left in the numerator as that placeholder all over. I already have y squared there, and now I have x to the positive 3. Because moving it from numerator to denominator changes the sign on the exponent from negative to positive. And this then is my final simplified result. So again, the goal in this was to take a look at expressions involving exponents and apply the properties of exponents to simplify them to their simplest form.